To understand the universe, look at the one thing connecting the massive stars in the night sky to everything in between, the atom. It interacts with all four fundamental forces of nature, acting as the ultimate bridge between the macroscopic world we live in and the microscopic quantum universe we cannot see. For a long time, we used the Bohr model, a central nucleus surrounded by electrons in rigid circular paths, like orbiting planets. But classically, any charged object moving in a circle is constantly accelerating and emitting radiation. Therefore, an orbiting electron would rapidly lose energy, spiral inward, and crash into the nucleus. If classical physics governed the atom, that inward spiral would take a fraction of a second. Every piece of matter in the universe would collapse instantly. Since we are here to talk about it, the solar system model has to be wrong. We need a completely different set of rules to explain how reality holds itself together. This diagram shows exactly why electrons don't crash. They exhibit wave-particle duality, acting like standing waves. Just like plucking a guitar string, an electron forms a continuous wave pattern around the nucleus, shown on the left, rather than the broken pattern on the right. Because the electron behaves like a wave smeared out across space, it doesn't have a single pinpoint physical location at any given time. This brings us to a strict limit of nature called the Heisenberg uncertainty principle. Werner Heisenberg proved that it is physically impossible to simultaneously know both the exact position of an electron and its momentum. It is a mathematical trap. If you calculate an electron's position with high accuracy, you inherently create a massive level of uncertainty about its energy. You can pin down where it is, or you can pin down where it is going, but never both at the same time. Because we can never track an exact path, the old idea of a predictable, planetary orbit is useless at the microscopic scale. Instead of tracking paths, we have to calculate the raw probability of where an electron is most likely to be found. So how do you measure a probability cloud? In 1926, an Austrian physicist named Erwin Schrödinger provided the mathematical tool to do exactly that. This equation is the time-dependent Schrödinger equation. The solutions to this math give us wave functions. Instead of flat physical tracks, these functions describe the electron as a matter wave, generating three-dimensional clouds that map out where an electron probably is. We call these probability zones atomic orbitals. Categorized by letters like S, P, and D, they take on highly peculiar shapes. They start as simple spheres, but as you add energy, they stretch into distinct elongated lobes and complex rings. With overlapping probability clouds, the atom should be total chaos. It isn't, thanks to the Pauli exclusion principle. No two electrons share the exact same quantum state. Inside an orbital, a pair adopts opposite up and down spins. Then the orbital is locked. This strict mathematical architecture creates a layered atmosphere of probability, with every electron confined within rigid, quantum boundaries. This graph illustrates how wave functions are confined to specific energy states, marked here as n equals 1, 2, and 3. Because of strict quantum rules, electrons can only exist on these discrete energy levels, much like distinct rungs on a ladder. There are no in-between states. This chart shows the probability density peaks for those exact energy states. Because the boundaries between them are absolute, moving between them requires a quantum leap. When an electron drops from a higher energy rung to a lower one, it releases its excess energy by firing off a photon, a packet of light, whose energy exactly matches the gap it just crossed. This spectrum reveals the specific wavelengths of visible light, measured in nanometers. Because the energy gaps in every element are unique, the photons they release have exact, predictable colors. These specific light gaps create unique spectral lines, acting as an immutable barcode, an atomic fingerprint for every element in existence. This lets scientists look at distant stars and galaxies to know exactly what they're made of. By simply reading the light passing through their telescopes, they can decode the exact chemical composition of objects millions of light years away. Replacing physical orbits with probabilistic math provided a way to calculate the stability of matter. This framework explains why atoms don't collapse and gives us the means to map stellar chemistry.